we don't have data. We don't know the truth. We don't know how well our things work because we don't have anything to prove them with. And we are all the time approximating statistics of interest, like this thing measuring, oh, let's assume this is the truth, let's measure something. We are not measuring what we want to. We are all the time approximating that just by doing something that we can with the data. We're just making do with the data we have. And so, good requirements that we should have to be able to carry out this kind of research is a preferably unlimited supply of data. There you see the simulation coming in, right? We need to know the true mean scores. That's the key to the whole thing. It would be nice if we could control the statistical assumptions to say how much of a problem the normality assumption poses to our problems. Need to maintain the distributions of the systems, how the systems are, how the systems depend on each other, what the dependencies are between the systems, and of course make it realistic, right? So let's go to simulation, right? And let's simulate from previous data. So let's say that I have a previous collection, let's call it X again, and it's going to be the matrix of system by topic, or topic by system scores, right? So something like for precision at 10, this system on this topic, this system on this topic, system on topic, etc., etc., right? So the observations that we have in an experiment, in an evaluation experiment, is just each of the individual scores for a topic. So the score for system 1 on topic, system 2 on the same topic, all the systems for that topic. That is one observation of an evaluation experiment, right? And we have many observations, as many as topic we have, right? And so the idea is let's fit the model M to all those observations that we have, and then let's generate observations from that model that we create, so that we can simulate new topics, a new random topic, and by that I mean the scores that the system would have had on that topic, right? And repeat as many times as we want. So again, from existing data, let's build a model so that we can generate new data from that model, and of course make it realistic. Right? Am I doing in time? Left. Oh. Okay. So if we simulate data like this, then by construction, in that model, is hardwired the true score of the system. We want to know. It's hardwired into the model that we want to have. So beforehand, we can know that the mu sub I, the true score of a system, is going to be the expected value of the data that I'm simulating. And that's what I want to have. And so, in fact, by doing things this way, we're going to say that it's just what we observed in the data set. Let's fix it to be the mean score that we have. Let's assume it is, and let's simulate realistic data with that assumption holding there, so that we can do all the research that we've been talking about before. We're going to see now. And so by no means I'm claiming that that model is modeling the reality or how systems really are in the true world. No, I'm not saying that. I don't want to get into that. What I'm saying is that it's just a realistic model resembling realistic data. I don't care if it's a good model for the systems we have already. I'm just saying it's a model that gives me realistic data that's going to be input to my evaluation research. And so for that, we can use something called copulas. And if you don't know where the name comes from, I suggest you go to Wikipedia because it's not what you think it is. And so, in essence, a copula is a model of the joint distribution of systems. So that's what we want to have, right? It's a joint distribution of the systems. And so, a copula model allows us to model it separately. On the one hand, the marginal, that is the distribution of each of the systems individually, regardless of the others. And on the other side, we model the dependency between all of them. And so that distribution that we have here for all the systems, it becomes something like this. It depends just on the distribution of each of the particular systems, plus a copula that models the dependency. Right? So we are going to separate those two things, each system individually, and then all of them together, the dependencies. And so a copula, if you want to say it, is a joint distribution whose marginals are uniform random variables. If you want to see it this way, I like to see it this way. We are not modeling the actual scores, we are modeling the quantiles of the scores, and you're going to see why that's a good idea. And so the idea is, we fit the distribution for each of the systems, the F sub S's, all the systems independent of the others, and then we transform them to pseudo observations, right? Something called the interval transform. So what we do is we get each of the scores, pass it through the distribution for that system, and what we get is a uniform random variable. Okay? Fit the copular model to each of those uniform pseudo-observations. Then we have the model that we wanted. And so to simulate, we generate a pseudo-observation from the copula and do it backwards. We go through the quantum function, and we get a new observation, a random observation for that system, following the same distribution from above. So that's how this thing works. It works by modeling a copula with the uniform distributions that we saw before, right? And again, you repeat this as many times as you want. And this is just a way of simulating new topics, as many as you want, maintaining the distributions and the dependency between the systems. That's what we want to have. And what is the true score of a system? It's hard-coded over there in the distribution of the system, right? The thing is, this has to be realistic. And so our first attempt to make this happen was to start from the model that we saw before, but now the system effect is going to be fixed because we are hard-coding that to be what we observed in the existing data. And then the topic effect and the residual are going to be random. And that to me is going to be observation from the evaluation experiment. It's going to be that vector of the topic effect and then the residual for system 1, system 2, system 3, system 4, such that you get that vector, you plug it into the formula, and you get the final score, right? And so we use Gaussian copula, which only models the correlation between systems. That's not a good model for dependency, but it's what we did first. And for the margins, we use kernel density estimation. So we just feed a kitty to the distribution, you get the function, and we feed the copula separately, the Gaussian copula, and start simulating from there. We're going to see an example now. And the good thing about this is that it allows us to control all the statistical assumptions, to see how much of a problem we have because we don't have Gaussian scores, right? It's actually surprising. So I'm just going to go over it just in a few places. The thing is that we want to simulate, you see, from the existing data, and not that I have to jump, from the existing data and the number of topics that we want to simulate. And what we do is, first of all, fix the true scores. That's what we want to have beforehand, so we fix it there. And then if we want to have same variances, then we force the same variances into the residuals. Let's forget about it, okay? But that's the key point. We are fixing this beforehand. That's what we want to know. And then we feed the distribution, we see, for the residuals, for the topics. Then we compute the covariance matrix. If we don't want the correlated effects, then just set all of those to 0 and you don't have correlations. If you don't want to have random sample, you do something. Here is where we work with the copula. Let's skip it. And in the end, this is where we build our final observation. So we got a random uniform from the copula, pass it through the quantum distribution, and we get an observation. The same for another system, another system, another system, and topics. And we get a final observation from the copula, maintaining the same marginal distribution for the systems and the dependency that we want to model. We plug those numbers into the model that we saw before, and we go. We have a final observation from that model that is supposed to be modeling something realistic. More or less, you get the idea, right? And in different places, depending on what you want to assume or not, then you have to tweak different things. So, okay, let's go back to the simulation, the reliability problem, and let's use this to study that problem and see what happens. This is what it gets really exciting, for me at least. I don't know. So, now we have an unlimited supply of realistic data from which we know beforehand the expected true scores. So now we can study this, the reliability problem, right? And I see that you're eager to see the results. And so let's compute experimentally the bias of all those ways that we saw before of estimating how good my collection is. And in this case, we run it in a paper with 4 different collections for TREC. And we chose these 3 in particular because their size is more or less representative of what we have in TREC. And also in terms of difficulty, so what is the system effect, the topic effect, etc. These are like an easy data set. So this one is easy to see what systems are good. This is like a medium one, and this is like a hard one. In this task, it's really difficult to see what systems are good. Right? And then we have one in which we have reciprocal rank. That one that was obviously non-Gaussian distribution. So let's simulate from this and see what happens. So the first case, where we have a collection and we wanted to know how accurate the collection is. So what we do, Chrome is out of date. Okay. First time I say that, anyway. Someone is hacking my computer. So for each existing collection of those that we had, then let's simulate 100 different collections of different sizes, of 5, 10, 15 different sizes of collections, up to 500. Okay? But only under the assumptions that we are supposed to have. So non-normal distributions, different variances, correlated effects, and random sampling. This is what we are supposed to have in information retrieval. So let's simulate from it. Right? And now that we have a collection simulated, and we know the true scores because they are hard-coded into the model to simulate, we can actually compute these things. So this is the true score we can compute. This is the estimated score computed as we saw before. What is the bias? What I told you before. Am I lying to you now? I tell you that your collection is too reliable when in fact it's not. Am I biased? I am the A. And so we have over 5,000 points. And I want to stress that we have over 5,000 points because we are simulating. We could never do this before in evaluation research because we don't have that many data. And so, by the way, we propose a different way of estimating the tau correlation. This is what actually started all this research. I said, I want to know what the correlation is with the truth, but I don't know how I can do this. I don't know how I can tell whether my model works well or not. So let's start simulating. This is what actually triggered all this research. And so here's an example. We're talking about the tau correlation. So here we have the bias, the estimated correlation minus the true correlation that we now know because we are simulating, right? And so if we are negative here, that means that we are underestimating the correlation. And we tend to say that the correlation is smaller than it actually is, or it's more unreliable than it actually is. So we're saying it should be larger, but actually it shouldn't, right? And so what we saw there are each of the 4 models that we saw before, and we see that they tend to have a negative bias. So then they tend to underestimate the reliability. So when we said before, oh, the TREC collections are not reliable, maybe they are. Because our way of simulate, of telling that, of telling what the expected correlation is, it's actually biased. And we see this huge bias in the estimators. You can see that the green one is going off, going from the negative to the positive. And the light blue one is the one that we proposed, that we see that kind of converges towards no bias once you have a decent amount of topics. So with another one, this is sensitivity, we see kind of the same thing. They are positively biased, so they are also underestimated, because here we actually want to have small scores. So if we have a positive bias, that means we are underestimating reliability. So we are in the same way. This is rho squared for each of the different collections, and again we are underestimating. So what we see is something interesting. All these different methods of saying how reliable your collection is, they are actually underestimating the scores, the truth. And so when we say that your collection is not reliable, maybe it is, because we are having this bias in all these kinds of estimated reliability. And so maybe our collections are not as bad as we thought. Maybe when we say that we need 200 topics, maybe just 150 is okay. And this is the first time that we are allowed to study these things and make these statements, because we know the truth, we are simulating from it, and it's realistic. And so what about the robustness assumptions? So what we do is simulate again from all the 16 combinations of assumptions and see how much each of those is affecting the results. So now we go to more than 80,000 data points. And throughout all the numbers, what we see is that for the tau correlation here and the tau IP correlation here, we see that it depends the most on the number of topics that you have in your collection. So if you have a small collection, don't trust too much what I tell you about the tau correlation. You need to have a lot of topics to start trusting me when I tell you your collection is good or not. But in that new estimator that we proposed, it goes from 20-something% to just 9. and 20-something% to just 9. So that means that that new way of estimating that we proposed is actually working a lot better than the other one. You can trust it even with small samples. The same problem we have here in the sensitivity. We have most of the error is coming from differences in the number of topics. Here in terms of error, we see also ours is doing a lot better than the other estimators. So we go from 0.02 to 0.01. So it's doing a lot better than what we used to. But in general, what we see is that in most of the cases, it just depends on the actual collection that you have. Actual topics, actual systems, and that's it. So, that means you have to go on a case-by-case basis. You can't just make a rule of thumb saying, oh, 100 topics is okay. No, you can't do that. Not even for different collections for the same task, with the same systems. You can't just do rules of thumbs like 50 topics, something like that, right? And something striking here is that we have a huge effect for one of the generalizability theory indexes saying that if you don't have random sampling, forget about it. Well, that was the accuracy of an existing collection. The second problem was, what is the expected accuracy of a collection design? What if I say my collection is going to be 100 topics, but I still don't have those 100 topics? How reliable is that design going to be? Is 100 enough? Should I go for 200, 300? And so the question here is something similar. We simulate from an existing collection, create 100 different collections, and again compute the expected over collections of the estimated reliability minus the actual reliability when we go for collections of 5, 10, 15, 20, etc. So the thing is, I get a collection of 5, and I want to estimate 10, 15, 20, 30, etc. Then I go to collections of 10, and I want to estimate 5, 10, 15, 20, 30, etc. Collections of 15, and from that estimate more and more. So now this is even more interesting. So for instance, here we have one of the estimators for the tau correlation, and the red line here says our existing data is only 5 topics. We are building a new collection. This is the first time we are doing this. How good are 5 topics? So you see that it's not very good, right? It's giving a bias like of 0.4. That's a huge bias, right? But the more interesting thing is that if you have only 5 data points, it doesn't matter how large your collection do you want it to be. It doesn't get close to 0. So if you have only 5 points, of 5 topics, then it doesn't matter what number you're going for. You're biased from the start. 5 topics are not enough. Let's say we go for 10, the red one, the green one, and you're doing better, but you see that constant bias. You never go towards 0. And then you get more topics, 50, 100, etc. And so what we see here is that the defining factor is how much data you already have. Not how much data you want to have, how much you already have. Everything depends on that, how much data you have. And what we are saying is, unless you have already like 50 or 100, you can't trust it. And that's bad news again. So we need already a full collection before we start making decisions about that same collection. We see same problems here with different estimators of the tau correlation. The other one is going crazy. And this is the one we proposed. And you see it's a lot nicer, right? It goes actually towards 0. So what it's saying is, in the case of only 5 topics to start with, then it actually tends to converge towards 0. And if you get 10 topics, it's even closer, and it goes even faster towards 0. And if you get 20, 15, etc., you go towards 0. So with this estimator, you can trust the results that you have. So if you get a collection of only 10 topics here, then it's telling you that the bias that I have is only about 0.1. But if you want to estimate how good your collection is going to be with 100 topics or 50 or so, then your error is going to be a lot lower than in the other methods. So actually here, we are doing a lot better. We have a new way of measuring all this that is actually less sensitive to the initial data that we have, and that works marvelous with small data sets, which is what we want to have. I'm building the collection, I don't have too much data, so I can use something like this. And so again, they are clearly underestimating the reliability of the collections because they have that negative bias, except for mine that has a positive bias. So it's especially worrisome when building a new collection. You can't trust what you have because you have still too few data points. But our proposed estimator worked well. Now again, we go through the robustness thing, how robust those things are to the different assumptions. And we see again that the normality assumption, the equal variance assumption, they don't really affect the results. So that's good. That means we can do all these things assuming certain things, certain assumptions like normal distributions, and we don't really care because it doesn't seem to be a good problem, a large problem. But where it does depend on is the number of topics that you have and that you want to extrapolate on. That's where most of the variability is in these estimators, right? Except, you see here only 2%, 1%, 2%, 1% in my estimator, in the one that we proposed. It doesn't really depend on the actual number of topics that you have now. Let's skip. This actually says that it does depend on the random sampling and correlated effects, which you should have. And the errors are a lot smaller. You see that now we go from 0.03 of error to less than 0.01. So that means it's working a lot better than the others, as we could see in the graphs. Let's keep moving. Okay, so new improvements are on the way, of course. That's something that we published already, and there's something that has been in the drawer for some time now. Hopefully someday it's going to go out of the drawer into peer review. And it's a lot of improvements into this way of simulation. One of the improvements is drop the Gaussian copulas and go for something called bind copulas. And the good thing about the bind copulas is that they model the tail dependence between the system distributions a lot better. So the Gaussian copulas only model the correlation. So you know we have these nice symmetric distributions, but that's not the kind of data we have. We have things with really long tails. And so the bind copulas are going to be better to model the dependence. Modeling system distributions directly rather than the topic effects that we saw before is going to be simpler. It actually is a lot simpler. And it's easier to control the assumptions. Respect the support of the distributions as derived from the effectiveness measure. So in all this I've been showing you, we said we had kernel density estimation to fit the model to the distributions. But if you have something like precision at 10, you can't use kernel density estimation there because that's a discrete random variable. Precision at 10 is 0, 0.1, 0.2, 0.3, 0.4, all the way up to 1. That's not a real number, so those models are not really representing the truth here. And so we build different statistical machinery to fit models to continuous data, to discrete data with non-standard supports, a lot of different ways of actually being more fitting better models to the true distributions of the systems. And have a mechanism to shape the distributions to some view that we want to have, and include other effects like different effectiveness measures at the same time, or more systems, more assessors, etc., etc. Different ways of plugging more components into this whole simulation stuff so that we can carry out different research with different models, with different data. And so just finishing, something that we saw is that the previous studies don't replicate. So we saw before that there is a lot of research that was limited by this absence of data with these characteristics. And one study in particular was looking into how well we estimate the variability of systems as we are building collections, as we are making more and more judgments and adding more and more topics. And one thing they found is that they're actually biased. So in all these cases that we've been speaking before of building a new collection, what they found is that in different ways they propose to measure the variability of systems, they're all biased. So they did resampling, what we said, one collection, another collection, measure, etc., etc. And so their conclusion was, we don't really know how to measure this, and we can't do it because it's biased. Look at the plot, right? Turns out that it's actually an artifact of the data they are using, of the way we've been doing this kind of research before without simulation. It's not really a problem of estimating the variability. It's a problem of the data we are using in our research. And so if we use simulation for real, simulating new topics for real, that effect disappears. So that is at least one conclusion, for instance, saying we don't know how to do that. That is actually a problem of the lack of data that we had before because of simulation. If we do have that data, we see that that problem doesn't actually exist. Another thing is, for instance, significance testing. There are many studies, mine included, suggesting that we are committing less than 5% errors because, again, of all the statistical assumptions, etc. Well, it turns out that if you do an experiment with simulated data, running the actual numbers that you want to run, and measuring actually what you want to measure, we are in the 5%. So we are making just as many errors as we are supposed to. So that is, again, some research that is just invalidated. So they were measuring something that was a problem of the lack of data that we had before, not an actual problem in information retrieval. So my question is, if we start looking into all these things now with this new data that we have available, how much of the previous data or the previous research is going to be invalidated? How many of the different things that we learned with the years are going to be invalidated now that we have these tools with us? And so, yeah, I'm going to skip it because I have to go, right? We took it even further and we improved the data estimator that we saw. That's